The American Association of Retired Persons claims that the proportion of male senior citizens who say they eat the daily recommended number of servings of vegetables and the proportion of female senior citizens who say they eat the daily recommended number of servings of vegetables are the same. That's what they say. In a survey, all right, so we have males and females. These are seniors. We're taking a random sample from each group. And for the males, in a survey of 5168 males, the number that said they eat the recommended number of servings of vegetables was 2164. So we can calculate p hat by dividing those two to come up with a percentage. For females, in a survey of 6158 females, we had 2681 said they eat the recommended number of servings of vegetables. So this is the survey that basically says, you know, the recommended number of servings of vegetables each day is 3. Do you eat that? And then they answer yes or no. So it's categorical variables, and we analyze that with proportions. P2 would then be the 2681 divided by the 6158. All right, so I'll just go ahead and quickly calculate those. And there they are, pretty close. It's about 0.419, 41.9% compared to 43.5%. So we see a difference between the two proportions, sample proportions, and our job is to decide if that observed difference is statistically significant. So we always want to write this stuff down, because this is what really determines if we do have a difference. We've got alpha, 0.10, assume the random samples are independent. So now we're going to go through the steps from section 11.1. Step 1 is to write the hypotheses. And in this test, we're always saying that the two proportions, the proportion of male seniors in P2 would be the proportion of female seniors who say they eat the daily recommended number of servings of vegetables. And by saying that P1 is equal to P2, we're saying that these two proportions are the same. So here is our claim. And if they're not equal, the alternative would be that they're not equal. So P1 equals the proportion of male seniors that eat the recommended number of servings. We always define the variables in great detail of vegetables. And I'm going to just abbreviate P2 here. All right, so it's still a proportion, but it's a proportion of females. And then everything else is the same. All right, the second step is to identify the level of significance. It's right up here, 0.10. And 3, up at the top of that, this is where we gather the evidence that we need to help us make the decision. And there's a couple of different ways to do it. If you use one prop z-test, that is, use technology to calculate the test statistic and p-value, then you have to enter in the x1, n1, x2, n2, these numbers over here that were given to us in the problem. And then you need to specify the alternative hypothesis. And in this case, the alternative hypothesis is not equal to P2. So we're going to select that one. And then from here, you'll calculate the Z test statistic and the p-value. All right, you need to make sure you get these in the right order. Otherwise, there'll be an error. Okay, let's go ahead and calculate that. All right, so in the test menu all the way down to number 6. And then we're going to enter these numbers. And then the not equal to. Test statistic and p-value. So I'll write those down. It's negative. Oops. I'll round it to 3 decimal places. And the p-value is this number here, rounded, again, to 3 decimal places. You'll see that our sample proportions, P1 hat and P2 hat, are calculated. And then the overall pooled proportion is somewhere between these 2 numbers. Step 4, we notice that P, which is 0.075, is less than alpha, which is 0.10. So therefore, the decision is to reject the null hypothesis. And then step number 5 is the conclusion. Since we're going to reject, the claim that the 2 are the same in favor of the alternative, which says that they're different in some way. So here you can see there's just a very small difference, 41.9%, 43.5%. But because these sample sizes were so large, this small difference that we observed turned out to be statistically significant, and we reject the null hypothesis. So there is evidence, enough evidence, sufficient evidence, lots of ways to say it, to reject the claim that male seniors and female seniors well, you want to say something about, eat the recommended number of servings of vegetable at the same rate. Let's just say it, are equal in their consumption of daily vegetables. All right, while we're here, I'm going to go ahead and do the confidence interval. And this confidence interval is always a confidence interval to estimate P1 minus P2. So it would be the difference in the 2 proportions. And so the calculator function we're going to use there is the 2prop z int. Right there. 2prop z int. All the numbers are still there. Our alpha was 0.10, and so that corresponds to a confidence level of 0.90. So we're going to calculate, and there you see. I'm going to write down the confidence interval and then remember what this means. All we need to know from this is that the lower bound is negative and the upper bound is negative. And so therefore P1 minus P2, this difference that we're estimating then is less than 0 because every number in this interval is negative. And that means the same thing, that P1 minus is less than P2. So if we add P2 to both sides here, we get this. So there's evidence based on this one sample, these two samples alone, that the proportion of male seniors that eat their recommended amount of vegetables is less than the amount of females. So even if we have a small difference, then we can have a statistically significant difference if our sample sizes are large enough. So this is saying men is less than women, which means men is not equal to women. The proportions are not equal. So this gives support for H1. The other thing I wanted to do is the reject region, the classical approach. We have alpha equals 0.10. It's a two-tailed test because of the not equal to sign. So we're going to put alpha over 2 over here, and another alpha over 2 over here. And we have two different critical regions. Over here we would reject if our test statistic falls out in here, or over here we would also reject if our test statistic falls over here. %90 on the inside, so you probably have these critical values memorized. If you do, great. .645. Okay, I'm looking in the chat now. Let's see. Yeah, it's 2prop. Critical value. Okay, I'm doing the critical values right now. Making the graph. Okay, so here's the graph. By the way, this is inverse norm because this is a z distribution. And one reason you can tell it's a z distribution, since we're using the 1prop z test, and we calculate a z critical value. So it's normal. And that's why we use the inverse norm. So the left area is 0.05. And over here, this is 0.95, because from this point over, you've got the 90% in here and then the 5% out here, 95 total. And this is going to be the positive version. All right, so these are the critical values, and they ask you to plot those on this graph. So here's all the setup. Then you go calculate the test statistic. That's your Z. See if I can get it in here. There it is right there. And when I plot that number on this scale, remember 0 is right in the middle, Z-score scale. This is a Z-score as well. The numbers, Z of alpha over 2. Same critical values we would use in a confidence interval. Here's 0, here's negative 1.645 and negative 1.783 is our, this is called the test statistic. And it falls in this region here, which is the reject region. So once again, by this test, we would reject just like we did using the p-value and the confidence interval. It's called the classical approach. Okay, let's take a look. We had a random sample 8 years ago. You had 27.5% of Canadians back then had college degrees. And then in a recent year, it looks like it shrunk to 23%. Here's the graph that you would set up as soon as you know alpha is equal to 0.05, and it's a two-tailed test. So just like our previous example, area on both sides, but now the left area and the right area is 0.025. In our previous problem, it was 0.05. Since it's 0.025 this time, you want to use the inverse norm of 0.025. Again, that's a critical value. That sets our line in the sand that determines where the most extreme 5% of the samples would be if P1 and P2 are in fact equal. So we're going to reject the claim. Can you reject the claim that the proportions were different? So we're going to turn that question around and just say the claim is that the proportions are different. And if they're different, then this time the claim goes in the alternative hypothesis. If you use 2-prop z-test, you get this test statistic and this p-value. P is greater than alpha, so we do not reject the null hypothesis. And there's one way to write the conclusion.